So in the previous module, we were looking at the application of variation treatment to simple systems for which the actual solution or analytical solution is feasible. And then we were looking at the feasibility of getting the eigenvalue and eigenfunction very close to the actual value or not. In the previous module, I applied the two trial functions to the hydrogen atom. One was exponential minus Cr, another was exponential minus alpha r square. And we found the value of C and alpha, that is variation parameter. And we found that exponential minus Cr gives you the exact energy which we can obtain from the analytical solution of the Schrodinger wave equation, because exponential minus Cr is same as exponential minus r divided by a naught, which is the real function, which is the actual function which we obtain from the solution of Schrodinger wave equation. But when we go for another trial function, exponential minus alpha r square, we got an energy very close to the ground state energy, but we did not get the actual ground state energy, because this alpha exponential minus alpha r square is not the same function. And out of these two trial functions, so we can say that exponential minus Cr is a better trial function than exponential minus alpha r square for the hydrogen atom. So with these two trial functions, you can do the comparison. Okay. Now what we do, that if you do variation treatment of particle in a one-dimensional box, then this also we can do. And we can, you know that for one-dimensional box, if you solve the Schrodinger wave equation, you have a normalized solution which is root 2 by a sine n pi x upon a, and for energy you have an equation En is equal to n square h square divided by 8 m a square. The solution is known to you. And I said you in the previous module that for guessing a trial function, what is important is that you look at the boundary condition. So the boundary condition of the particle in a one-dimensional box is of the dimension a is that x is equal to at x is equal to 0, the function is 0, and at x is equal to a also the function is 0. Okay. So any function which obeys this boundary condition could be theoretically a trial function for the particle in a one-dimensional box. And for that matter, I have written two functions, 1 and 2, which is x into L minus x, and another is x into L square minus x square. And if you look at this, at x is equal to 0, the function 1 will be 0, and at x is equal to L also the function will be 0. Since I have written L, so you can write instead of L here. Instead of A, you write L. Okay. So x is equal to L minus L, so it will be 0. And if you look at the function number 2, then again this also follows the boundary condition. At x is equal to 0, the function 2 is 0, and x is equal to L also, the function is 0. So both these equation 1 and equation 2 could be a trial function for particle in a one-dimensional box. Okay. For finding out this solution, psi n is equal to root 2 by L sine n pi x divided by L, and for that matter, let me write it. It's L. It's L. It's L square. Okay. So this is also L. Sorry. Okay. So for finding out the solution, we suppose that the potential energy within the box is equal to 0. So if the potential energy is equal to 0, then what is the Hamiltonian? Hamiltonian is minus h cross square divided by 2m d square by dx square, because we have only one dimension here. It's a particle in a one-dimensional box. So the Hamiltonian is this one, minus h cross square divided by 2m d square by dx square. And again, you have to do variation treatment. So you will use the Rayleigh ratio to find out the energy, and this Rayleigh ratio will be like this one: psi star h psi dx divided by psi star psi divided by dx from 0 to L. Now the limit of the integral is 0 to L. And so what you write? Psi star minus h cross square divided by 2m d square by dx square psi dx, and here it will be psi star psi dx. Okay? This you can write very easily. If you put the value of trial functions for psi is equal to x L minus x then your numerator becomes equal to x into L minus x and x into L minus x. In between you have the Hamiltonian h. Okay. So what you need to differentiate this equation x into L minus x. So we can write xl minus x square and minus h cross square divided by 2m ddx. So it will be one differentiation will give you xl will become L and x square will become 2x. The second differentiation, L is a constant, so it will be 0 and 2x will become 2. Okay. So after second differentiation you get this one, 2 and 2 will go, you will have n square h cross square divided by 2m will be outside and you will have xl minus x square dx. Now you have to integrate this equation. So two integrals you have xl minus x square. So xl will be, L will be constant outside, so differentiation of x dx, and the second integral of x dx, and then the second integral will be x square dx. That's very easy to do and all of you know that. You get this numerator is equal to n square h cross square divided by m L cube divided by 6. This is the numerator. Okay. In denominator you have, denominator will have normalization and then you will have x into, you see, x into L minus x. So twice you have to write, so you can write L minus x square dx. This is your denominator. You do not have h in the denominator. That's normalization condition is in the denominator. Okay. So if you put this this value, then what you need? You multiply by x square and it's a minus b whole square. So open it up and then multiply by x square. What you get? X square L square minus 2L x cube plus x4 dx. So you have the integral of x square dx, integral of x cube dx and integral of x4 dx. And finally what you get, what the value is n raised to the n square L raised to the 5 divided by 30. So you do have the numerator also, you do have the denominator also, and if you put these values, numerator and denominator, then what you get is 5h square 4 pi square ml square. So 5h square 4 pi ml square could be written as 10h square pi square 8 ml square. So if you take this h square divided by 8 ml square within bracket, then you will have to divide 10 divided by 8 pi square, and this comes out to be 1.01423 h square divided by 8 ml square, and this comes out to be 0.12677 h square divided by ml square. Okay. So this is the value which we of the energy which you obtain from the from this energy. I think this was the x into L minus x. Okay, this trial function, phi trial was x into L minus x. What is the actual energy? You remember, actual energy is n square h square divided by 8 ml square. Okay, actual energy is n square h square divided by 8 ml square, and for ground state n is equal to 1, so it is h square divided by 8 ml square, and 1 divided by 8 is actually 0.125. So if you take this is your eigenfunction, this is your eigenvalue, and this is your eigenvalue which you obtain when you apply Schrodinger wave equation to particle in a one-dimensional box. When you use variation treatment and you use a trial function x into L minus x, the value of energy which you obtain is 0.12677 h square divided by ml square. You see how close we are. Okay. If you look at the difference, then it will be it's 0.12677 and it is 0.125. The error is only approximately 1.4%. That is why variation treatment is a very good method for finding out the eigenvalue and the eigenfunction for those systems for which we cannot have an analytical solution of the Schrodinger wave equation, because we are very close to this one. This trial function x into L minus x has no correlation with the actual wave function root 2 by L sin n pi x divided by L. Okay, but the only thing which is common in between these two is that this function also becomes 0 at x is equal to 0 and L is equal to 0, and this function also becomes 0 at x is equal to 0 and L is equal to 0. So only boundary condition has guided you to get a trial function like psi is equal to x into L minus x, and with this boundary condition we got an energy which is very close to the actual energy of the particle in a one-dimensional box. Okay, and we are only away from the actual value by 1.4%. The error is very low, 1.4%. Okay, what will happen if instead of this we use another function x into L square minus x square, and I have not given any solution for this. You will do it on your own, and for just in order to make you sure, when you calculate the numerator, your numerator should be this one, and when you calculate the denominator, your denominator should be this one, because enough of the derivations we did and all the steps is already done earlier. Now you look at this one. When you use this x into L square minus x square and you find out the energy, it is 0.1331125 h square divided by m square. Okay, so initially the best value was, the actual value was 0.125 h square divided by m square. Then with x into L minus x we got energy equal to 0.12677, and then with x into L square minus x square you get an energy equal to 0.133. So psi x into L minus x gives a ground state energy which is only 1.4% higher than the actual energy. Okay, but with x into L minus x into L square minus x square, what you get? An energy which is 6% higher than the actual energy. So out of the two functions, x into L minus x is a better function, better trial function than x into L square minus x square. Sorry. L square minus x square. Okay, so this is how we use the variation methods for finding out the energy and the eigenfunction for the particle. This is the summary of. Now another trial function which I have written here, but I have not given you anything, numerator, denominator, nothing I have given you, and you will do it as a homework, and what you should find out is the final energy, which is 0.152 h square divided by m square. So look at this one, the 0.126 with this trial function, 0.133 with this trial function, and with this trial function, which is your homework, you get an energy equal to 0.152. And see the energy error, it's a 1.4% higher energy than the ground state, it is 6% higher energy than the ground state, it is 21.6% percent energy higher than the ground state. So what does it mean? All trial functions are not good trial functions. Only those trial functions which gives you an energy which is very close or to the ground state is a good trial function. So out of these three, if somebody asks you which is the best trial function for the particle in a one-dimensional box, you say the best trial function is psi is equal to x into L minus x. The boundary condition is fulfilled by all these three. Yet for all these functions, the function will become 0 at x is equal to 0, and the function will become 0 at x is equal to L x is equal to L. But the best trial function is this, because this gives you minimum error in the energy value. Okay, so this is how we use the Schrodinger wave, the variation treatment for particle in a one-dimensional box. So we applied variation treatment to hydrogen atom, we applied variation treatment to particle in a one-dimensional box. And in both the cases, I have used two different wave functions, two different trial functions for finding out the energy eigenvalue and the eigenfunction. Okay. What will happen if we, instead of this these systems, we have a system which is where more than one atomic orbitals combine, so that it is a molecule. And for that, for any molecular system, since it is made up of atoms, so we say we can use a trial a variation treatment called linear variation treatment. And in linear variation treatment, the what we say the trial function is expressed as a linear combination of the normalized orthogonal eigenfunction of the system. So since it is a linear combination of the function psi n, okay, so we say it to be a linear variation method, and the trial function is psi a. Okay. Now here what is the variation parameter? Variation parameter obviously is an. An is the variation parameter. So psi n is the function which is orthonormal set of functions from the same system, and then an is the contribution from these functions to the actual system. Okay. So again here also we are getting a trial function, but we are taking a function as a sum of different functions of the system, of the same system. So this is a linear variation treatment. Since it's linearly combined, okay, it's a linear combination. So it's called linear combination. So it's called linear variation treatment. If in addition to these terms, we can add other terms also, and that will make it non-linear variation treatment. We will not go into the details of those, but linear variation. In the previous variation treatment, we have just guessed a trial function from nowhere, very arbitrarily, just looking at the boundary condition. But here what we say, that we have some idea about the contribution in the system by some functions, and then we linearly combine those functions to give you a trial function. So this is so if you have a system where there's a role of psi a and psi b in the system, then what we can write? Psi trial we can write as C1 psi a plus C2 psi b. Now what does it mean? It means C1 and C2 are the variation parameter here. Okay, which will tell you, these coefficients will tell you that how much is the contribution from psi a and how much is the contribution from psi b, okay, to the actual system. Now if you have a trial function, then what is the rule? Use the Rayleigh ratio, find out the expectation value, then after finding the expectation value, which is also the function of variation parameter, you differentiate with the variation parameter and equate it to 0. That's what we did in the previous 4 examples, and here also we will be doing the same thing, but it will be a little different. Okay. So what we do? We can write the Rayleigh ratio as psi star h psi d tau divided by psi star psi d tau. So your function is C1 psi a plus C2 psi b, h C1 psi a plus C2 psi b d tau. We do know the system. So h I am not writing, Hamiltonian I am not writing, because I am writing a general equation which is applicable to any system. Okay. So but the only thing is this, that this particular system where you use this variation treatment should be made up of different functions. So here we have two functions, psi a and psi b. So we have written C1 psi a plus C2 psi b. C1 psi a plus C2 psi b, in between you have h, which is Hamiltonian. Then you can write C1 psi a plus C2 psi b and C1 psi a plus C2 psi b d tau as the denominator. And if you expand this one, what do you get? Well, you get C1 square psi a h psi a d tau plus C2 square psi b h psi b d tau plus 2 C1 C2 psi A H psi B d tau. This will be the numerator, and the denominator you have C1 square psi A d tau, C2 square psi B d tau, and 2 C1 C2 psi A psi B d tau. Now this equation, this ratio is a little cumbersome, so make it a little simple, and use some way out of writing these integrals. This integral, which is psi A H psi A d tau, is written as HAA, and psi B H psi B d tau is written as HBB. These two integrals are called Coulomb integral. Okay. When you have psi A H psi B d tau, it's called HAB, and this integral is called exchange integral or resonance integral. Okay. See the difference. Here both the wave functions are same, psi A and psi A, psi B and psi B. So it is Coulomb integral. If the wave function are different, psi A and psi B, then it's called exchange integral or resonance integral. A and B is only the nomenclature or definition. One can write 1 and 2, one can write I and J, whatever you want you can write, and in all different books you will find different kind of nomenclature there. You write A or B, or 1 or 2, or I or J, whatever you want you can write. Okay. So these integrals HAA, HBB are Coulomb integral, and HAB is exchange integral. Now these integrals SAA d tau is equal to SA, SBB d tau is equal to SBB, and SAB d tau is equal to SAB, and this integral is called overlap integral. These integrals, if psi A and psi B are orthonormal, if psi A and psi B are already normalized, then this is the normalization condition. So SA will be equal to 1 and SBB will be equal to 1. Okay. So both these will be equal to 1 if they are normalized. If it is normalized, then this will be equal to 1, this will be equal to 1, provided it is normalized. Okay. So we can write this ratio, Rayleigh ratio, now in the simpler terms as C1 square HAA plus C2 square HBB plus 2 C1 C2 HAB plus C1 square SAA plus C2 square SBB plus 2 C1 C2 SAB. Okay. Now this equation could be, you can rearrange, and you can get C1 square SA plus C2 square SBB plus 2 C1 C2 SAB, and then C1 square like this one. Once you have this equation, then you can do, what you can do is you can differentiate with respect to the variation parameter, that is C1 and C2. So you unequate it to 0. So what you do, you differentiate energy with respect to C1 keeping C2 constant, you differentiate energy with respect to C2 keeping C1 constant and equating it to 0. Okay. And if you do this first with C1, then what do you get? You see what I have done. Del E by del C1 means I differentiated this term and I kept this constant, C1 square SA, C2 square SBB plus 2 C1 C2 SAB. So it's constant here. Okay. So I am talking about LHS. The way first we differentiated energy and kept the second term constant. If I write this as the first term and this as the second term. Okay. So I have differentiated first term, kept the second term constant. Now I will keep the first term constant, E is constant, and I will differentiate the second one. Remember, we are differentiating with respect to C1. So the first differential E is a constant, then C1 square SA will be 2C1 SA, after differentiating C1 square will become 2C1. Then the term is C2 square SBB. You do not have C1 here, so it's a constant term, it will become 0. Then you have 2 C1 C2 SAB. So differentiation of C1 with respect to C1 will be equal to 1 and it will be 2 C2 SAB. So LHS differentiation is fine. Now go for RHS. For RHS, if you do, it will be 2 C1 HA, then C2 square HB will become 0 and 2 C2 HAB. Now you see in this equation, in the last equation, this del E by del C1 you have to put equal to 0. So putting del E by del C1 equal to 0, this whole part will become 0. the first part will become 0, and finally what you get is an equation E2C1SA plus 2C2SAB plus 2C1HA plus, sorry, 1 plus is extra, so 2C2HAB. Okay. Then you have, if you rearrange, what you get, C1HAA minus SAA, C2HAB minus SAB, ESAB is equal to 0. This you obtain when you differentiate energy with respect to C1. If you do the same differentiation with respect to C2 and equate it to 0, what you get is C1HAB minus ESAB, C2HBB minus ESBB is equal to 0. So what you get two simultaneous linear equations with two different unknowns C1 and C2. Okay. Equation 1 and 2 are two simultaneous equations of two unknowns C1 and C2. And now what you can do, according to the principle of linear algebra, the essential condition for these equations to have a non-trivial solution, that is C1 and C2 is not equal to 0, is that the determinant of the coefficients of C1 and C2 should vanish. Okay. So this principle we use, and we can write a determinant which will be equal to 0. So the determinant of the coefficients of C1 and C2. And what is the coefficients of C1 and C2? The first coefficient is HAA minus ESA. Then second coefficient is HAB minus ESAB. Then third coefficient is HAB minus ESAB. And the fourth coefficient is HBB minus SAB. So if you write a 2 by 2 determinant with these coefficients, that determinant should vanish. That means that determinant value should be equal to 0. So we write a determinant like this one. HAA minus ESA, HAB minus ESAB, HAB minus ESAB, HBB minus ESAB is equal to 0. This determinant is called secular determinant. This we obtained when we have taken the psi trial as C1 psi A plus C2 psi B. You can change this, and you can, it's a summation of, so what is the linear variation treatment is, that psi trial you can take as summation of Ci psi I. Okay. So you can take 3 functions, you can take 4 functions, you can take 5 functions. And if you do the similar calculation for 3 functions, C1 psi 1 plus C2 psi 2 plus C3 psi 3, then what you will have to do? You will have to calculate the energy, and then you will have to differentiate it with respect to C1, then with respect to C2, then with respect to C3, and so you will get 3 simultaneous equations, and the coefficients of all C1, C2 and C3 will form a determinant with 3 unknowns. 3 equations with 3 unknowns you will have. So the coefficients of C1 and C2, C3 will form a determinant which must vanish. Why it must vanish? Because then only the C1 and C2 and C3 will have non-zero values, and it will give you the contribution to the system. So you will have a 3 by 3 determinant for such system. If you go for 4 combination of 4 orbitals or 4 functions, then you will get a 4 by 4 determinants. If you go for 6 functions combination, this summation is of 6 functions, then you will get a 6 by 6 determinant. And all these determinants are called secular determinant. Okay. These HAA, HBB and HAB, which is called Coulomb's integral and exchange integral respectively, and SAB are very important quantity for doing the molecular orbital theory and finding out the energy of molecular orbital systems. Okay. So what we can do, but we will go and we will use these secular determinants for the molecular orbital theory in the latter part of the modules. But for the time being, we were talking about the system of particle in a one-dimensional box. So we have found that this is a trial function and this also is a trial function. So if you use these trial functions, then what you can get? You can, as a variation treatment, you can combine these two together. So one of the function, your psi A is this one, or your psi B is this one, no? Psi 1 and psi 2 I have written. So you can write the 2 by, without going into the details of how to get the secular determinant. Now you can use directly, since it's a two function, so 2 by 2 determinant you will get, and you can write H11 minus ES11, H12 minus ES12, and H21 minus ES21, H22 minus ES22. And if it is so, then you know what is the value of H11. H11 is psi 1 H psi 1. So it will be x into L minus x, H x into L minus x deta. What is H22? The second function will be there, x square L minus x whole square, H Hamiltonian, then x square L minus x square deta. For H12 you have one function is x into L minus x, and of course the limit you will write, it will be 0 to L. Okay, if you can write, I have not written limit anywhere, but you can write the integral limit is this one, x square into L minus x square. Okay, so if you use these values, and so for the same reason, S11, S22 and S12 also you can write x into L minus x, x into L minus x deta. Here h is not there, rest of the thing is same. Okay, then you will find out these integrals, all these 6 integrals value I have given you. I will not do it, you will do it yourself, and you should find that you get this value H11, H12, H22, S11, S12 and S22. And if you use these values in the determinant, then you can use H11 minus E S11, H22 minus E S22, H21 minus E S21, H22 minus E S22. Okay, and then for the simplifying the equations, we suppose the box length is unit length, and we multiply it by m by h cross square, then you get this determinant. Obviously all a we go here there's some confusion should not be there. I have written it in the form of a, and what is the function is here L. So I am writing this, you should always remember a is equal to L. This I am using as synonym, it is the dimension of the box. So since trial function was L, so this could be L cube, this could be L5, this could be L7. So don't get confused from where A is coming. It's the same thing, L5, then L7, then L9, and thereafter you can. Okay. So here also all A will be equal to A, treat A, all A as L, and then what you get, then certainly A whether A or L it goes because it is the unit length. Okay. So multiplying m by h cross square will give you this one, and from this you can calculate the energy value, and finally what do you get? You get this energy value, epsilon I have written, but it's actually energy value. Okay. So it comes out to be this one. The actual value which comes out to be 4.93487 h cross square divided by m. Okay, or 0.125128 h square divided by m. What is the actual energy? The actual energy is 0.125 h square divided by m. Okay. So you see, when you use this variation treatment, linear variation treatment for the particle in a one-dimensional box, you are very close to the actual ground state energy. So gradually we started talking about variation treatment and then linear variation treatment. We did it the calculation with the individual functions also. We did this calculation with x into L minus x also. But we found that we are 1.4%, we get an energy which is 1.4% higher than the actual energy. And when you use linear variation treatment, that is only 0.1% higher. If of course it will always remain higher because it is not the actual function, but it's only 0.1% higher than the actual energy. So it's a very good approximation which we obtain from the linear variation treatment for particle in a one-dimensional box. Okay, I think this is the last slide, and in the next module I will talk about applying this variation treatment to molecules or simple molecules, H2+ molecule and so on. Okay, thank you.